Thank you very much, Greg. So Greg would be happy to answer a few questions if we have questions from the audience. Anybody wants to know something about their favorite virus?
Do you have a question over here in the red? Yes. No? Oh, okay. I thought I saw you waving.
There's one over here.
Oh, yes.
You said that there were 10 to the 31st bacteriophages in the world.
Yes.
How many different species or types?
You know, this is a great question. So the question was, all right, you have a 1 followed by 31 zeros of different viruses. And the question is, how many different types? That's just the types that infect bacteria. And within those, there's a huge number of different subcategories that we've barely scratched the surface for characterizing. I can't even give you a number. There might be just 10 to the 20 different types, but we don't know. We haven't done enough statistical analysis. We haven't collected enough examples and analyzed them to be able to give you a statistically robust answer to your question.
The question then is, you give me a big enough number. So
Yeah.
that's my follow-on question, which is, how can you hope to be efficient? Because there are about 3 times 10 to the 7th seconds in a year.
I know. Okay, this is a great question. That's a good question. Yeah, it's basically a back-of-the-envelope calculation. So the short answer is I'll never collect 10 to the 31 anything in my laboratory. That would take a lab the size of the state of California or something to do that. So I'm not even going to try on that one. But I can certainly sift through 1 trillion different things fairly quickly. Okay, so if I get 1 trillion different things and I get enough copies of each one, I'll on average in say an hour be able to get each one sampled within binding. Because the binding events I'm talking about are very, very fast. They're on the order of nanoseconds to milliseconds, somewhere in that range. So because the binding events are very, very quick, then I can feel some confidence that I'm sampling all those different events. So, but this is a really important question. It's something we actually spend quite a bit of time in designing our experiments thinking about. So, but I'm not going to get to 10 to the 31 anytime soon. 10 to the 12 is big enough for me. 1 trillion is a big enough number. So.
Another question over here.
Yeah, in blue.
Excellent presentation.
Thank you.
When you talk about prostate, your father,
Mm-hmm.
cancer, what
Yeah.
other cancers are you, does this applicability?
Yes, we're especially focused now on the cancers that we can find markers for in urine. So this specifically means cervical cancer, bladder cancer, urinary tract cancer, prostate cancer. Those are cancers where we can actually find the cancer-associated proteins in the urine. And we're going to start with those because there's the highest concentration of those proteins in urine. In the future, though, you can imagine moving to things like breast cancer because there are tiny, tiny little quantities of breast cancer-associated markers that are found in biological fluids. And so in theory, it might be possible. We have a ways to go, though, to get to that. So we're starting with the ones in bladder cancer. If we can diagnose bladder cancer, that would be a really big deal. So, sure, thank you. A question over here, Ev?
Do the good viruses you have in the lab ever mutate to
That's a great question. Yes, I get asked that a lot. So the question Ev is asking, I believe, is you make all these changes, you make 1 trillion different versions, what if they suddenly get loose and start infecting humans or something like that? I think first, we don't change them around to the point where they can no longer be recognized by the immune system. Your immune system has co-evolved alongside these viruses. They have existed as long as there were bacteria, or about as long as there were bacteria. So your immune system has gotten to the point where it's really good at recognizing these viruses. And we never take out those attributes that enable your immune system to recognize the viruses. Instead, we confer new attributes. So your immune system is always very, very good at wiping out these viruses. And that's why, incidentally, these are not going to be useful cures for disease. Okay, so I don't know, how many people in the room have read Aerosmith by Sinclair Lewis? Great book, by the way. Okay, yeah, I see a couple hands. So this is a great book, and it was written sometime in the 1920s. And in this book, it chronicles the life of a physician. And this physician is working at a place that's loosely described as Rockefeller University. And the physician has this idea of using these viruses to cure disease. The problem, and this was an idea that's been pursued for many years, especially in the former Soviet Union. The problem with that is that your immune system is really, really good at recognizing these viruses and wiping them out. So it hasn't worked very well. So the Aerosmith idea was a good one. It just hasn't worked out so well. And I saw another question over here somewhere. Yes, in the back.
How does the signal for PSMA vary with the concentration?
It's a linear, I didn't show you this, but we actually have a calibration plot. Actually, I think it was on one of the slides. Let me just show you. I think I have it on the slide. I can just go back. I didn't call attention to it, but it's right here. Here. On this plot right here, this is concentration of, in this case, an antibody that recognized the viruses. And you can see it's a linear correlation over here with concentration along the x-axis and the signal to noise along the y-axis. And then this is a non-binding antibody, an antibody we know doesn't bind the virus. And at different concentrations, it remains with a signal to noise of 0. So, good question. All right. Well,
Okay, thank you very much.
Thanks.
Greg. So, a couple of things to finish up with. First of all, as you're leaving, if you don't already have one of these brochures that describes the entire program for the year, make sure you pick it up so you've got the dates you can put on your calendar for the different topics for our lecture series. And the other thing is that Greg is, as we talked about, going to take people on a tour through his lab. Guaranteed that you won't be infected, or if you're infected, your immune system will wipe out the virus. We thank you very much for being here, and we hope that we'll see you all in January. So thanks again for coming.